Right. Good afternoon, everyone, and welcome to our senior project presentation on the multiple applications physical therapy table. And again, my name is Jake, Ravina, Aaron, and Jared. Yeah, so just to go over what we're going to talk about for the next 20 minutes, we're going to start with the mat table background. What are the scope that's required for us to do? We're going to discuss a little bit about the previous year's senior projects. What did they accomplish and what are some of their drawbacks? We will pitch our initial design and prototype with SolidWorks and Inventor 3D models. We will discuss a little bit about the finite element analysis we did, the force analysis, and our material selection. We will then finally talk about the cost estimate and budget and give any further recommendations to further improve our current design.
So just a little bit about the background of the mat. Brian Sherritt, who's also our industrial mentor, came up with the Excellence in Rehabilitation in 2011 with the intention of developing a physical therapy equipment that would cater more towards the elderly and disabled. He found out that a lot of physical therapists were having a hard time working with patients due to the lack of space and time. And he also noted that a lot of these patients were sometimes uncomfortable or anxious because a lot of these activities were being done in public gyms. Hence, the mat was designed to ease those fears by providing a single piece of equipment with multiple functions. Here are some of the functions of the mat. Firstly, it's a manipulation and treatment table. This table is longer and wider than your usual table, which will allow physical therapists to work with patients more effectively. It also has a unique traction system, which utilizes both self and manual traction. The table is able to tilt up to 45 degrees and -7 degrees. The table doubles as a gravity-resistant lower extremities exercise platform. With the help of the foot panel at the bottom, patients can do exercises like squats safely at different angles. It also comes with a detachable pulley system, which again patients can use to do arm workouts like tricep extensions and curls. Here are some of the main requirements that we took into consideration when designing this table. Firstly, it has to be able to lift to at least a height of 30 to 36 inches and be lowered to a minimum of 18 inches above the ground. I say 18 inches because this is the standard wheelchair height, and patients who are wheelchair bound will find it easier to get themselves onto the table. The table has to tilt to 45 degrees, as this resembles 80% of the patient's body weight, and -7 degrees because it was found that this is the optimal tilt for patients who are heavier to adjust themselves when they're on the table. Lastly, it must be able to withstand a maximum of 500 pounds. Here are some of the previous designs. The one on the top was done by a group of professional engineers seeked out by Brian in 2019. They had a bunch of multi-level adjustable arms and 2 actuators that controlled the tilt and vertical movement. The one on the bottom over here was done by the 2021 senior design group. They had a main tower actuator that controlled the height of the table and a separate actuator that controlled the tilt of the table. Just like any other projects, there were certain drawbacks to these previous designs. As for the first one, they achieved all the height requirements, but it was not able to withstand the 500 pounds. And the second one done by the senior design last year, they had a very solid design when it came to maximizing stability, but they weren't able to reach the minimum height of 18 inches, and also their actuator system was very costly. The current prototype, however, is being used in a hospital at this time.
So the reason why we took on this project is, after hearing Brian's proposal, we learned that there is a niche market on the physical therapist table. And as Pravina said before, many physical therapists are using to treat their patients which may be physically impaired. Thus, making the first table ever to satisfy all the patient's needs would mean a lot for us and to Brian as well. And there are many aspects to learn and overcome from this project, such as brainstorming and coming up with a brand new design, material sourcing from Mac-Mastercard, and talking to many other actuator companies, budgeting, and finally building a one-to-one model. way we approach this problem is firstly identifying the main obstacle that the previous group has faced, which is trying to get the table long enough to 18 inch. We had done a lot of research on different tables, such as stretchers from hospital beds, and we decided that scissor lift type design is the best to both tilt and manipulate the table's height. The initial designs were drawn on SolidWorks, and using 3D printing techniques, a 1 to 10 scale of the 3D model was made to visualize for the mechanics of the table.
So for our initial design, we decided on 2 scissor legs that form an X across the base of the table. And they're attached with 2 sets of roller and track assemblies along the upper frame of the table. We did some initial calculations and determined that the lengths for each track would need to be 13.5 and 9.5 inches in order to reach the desired parameters. The next step was to determine the needed lengths and forces that would be required of the actuators. This was a bit tricky because these factors relied heavily on actuator placements. Many different configurations were simulated, and in the end, it was decided that 2 linear actuators with stroke lengths of 500 millimeters and forces of 8,000 newtons would achieve the desired results in the configuration that we've chosen. We began the testing of our chosen configuration by modeling it in SolidWorks to get the lengths correct and to make sure that the mechanisms worked the way that we wanted them to. Then we fabricated a 110 scale model using 3D printing techniques to prove that the mechanisms would work as they did in SolidWorks. Lastly, we built a 1-to-1 scale wooden model in order to identify any design flaws that would arise with actual fabrication of the design. We used wood instead of our final design choice of steel because it was less expensive and would allow us to quickly modify any design changes that were required. As you can see here, our first fabricated model did achieve all of the positions that were required. We built the frame out of standard 2x4s and got hardware from the local store. The track and roller assemblies were ordered from McMaster Car, and the actuators were salvaged from discarded hospital beds. Connectors so that the actuators could attach to the wooden frame were assembled using a 3D printer. Although we achieved all of the desired positions with the first model, it was found to be too unstable for practical use in the field. If any force was applied to the table frame in an uneven fashion, such as somebody getting onto or off of the table, the frame would shift in all directions and would rotate about the scissor arms by about 30 degrees in either direction. We determined the track and roller assembly to be the source of instability, as the rollers would allow the table frame to move even while the actuators were stationary. For the second model, we realized that one end of the table frame must be fixed directly to the scissor legs in order to increase rotational stability. We were able to do this by modifying the previous model and moving one of the roller and track assemblies to the lower portion of the scissor legs and fix that portion of the upper frame to the scissor legs. We also decided to move one of the linear actuators into a horizontal position that would push and pull the scissor legs in order to adjust height. This new design was also able to reach all of the desired positions. The stability of this design was significantly better than that of the previous, with rotational instability reduced to about 10% in either position. Even though the rotational instability had been decreased from the first model to the second, it was still too much for practical application. The issue was found to be that of an upper track and roller assembly, which still had unwanted free movement. The solution to these instabilities was to minimize or eliminate this unwanted movement. We determined that this could be done by replacing the upper track and roller assembly with that of an electronic sliding actuator. This would eliminate any unwanted movement, as the actuators would only move when told to do so. We reached out to many actuator companies, and unfortunately we were not able to get our hands on an electronic sliding actuator within the time frame for our prototype. It was determined that we could simulate the difference between the electric sliding actuators and the track and roller assemblies by using the grounded constraint in Autodesk Inventor to keep unwanted parts from moving. The images on the screen capture the rotational instability experienced from the track and roller assemblies when they are not grounded. However, all unwanted movement was eliminated and the table became stable enough for practical use when they were grounded. With the table only moving about 1 millimeter up and down on either side when any force is applied. This is going to be used as a proof of concept for our final design. And for our demonstration, we have included clamps near the scissor arms on the track and roller assemblies to prevent them from moving, acting as an electronic sliding actuator.
So SolidWorks was a big asset in our design process. Through SolidWorks, we can visualize our design and see if it met our tilt and height requirements. We could also optimize the track lengths, and some hardware parts are designed which we could then convert into a 3D printable model using software Kira. And this SolidWorks model was also used for our FEA analysis, which will be shown in the next slides.
Now I'll discuss a little bit about our SolidWorks simulations findings. So simulations were done for all 4 positions of the table, being the lowest, the highest, 45 degrees, and -7 degree tilt. And with 3 different loading conditions. So distributed load, front load, and end load. A safety factor of 3 is used in the weight conditions and bringing up the weight requirement to 1,500 pounds. The material used in the next 3 slides will be shown as AISI 1020 steel cold roll. That's what the table will probably be made out of. And it has a yield strength of 350 megapascals, which will be used to calculate the safety factor in the next 3 slides. This shows the table at its highest position of 30-inch. The maximum stress experienced by the table is around the scissor arm at the top of the table, and the safety factor is 2.25. Maximum displacement is found to be 0.6 millimeters at the middle of the table. Next, this is the table at 45-degree angle, and the maximum stress is also experienced in both the scissor arm of the table, being 360 megapascal. This brings the safety factor down to 0.97, and if most of you know, this would mean that this table actually fails under this type of loading conditions and position. We overestimated the weight requirements by 3 times to see if there's any weak points or which point would the table most likely fail first. And with this result, we can conclude that the scissor arm would be the first failing point of the table. And the maximum displacement is 3.5 millimeters on top of the table. And finally, this shows the table at a -7 degree. Maximum stress experienced by this table is 216 megapascal at a safety factor of 1.62. And the maximum displacement is 0.73 millimeters. We have also used multiple materials such as steel, titanium, and copper in our simulation. The stress experienced by all 3 materials are relatively the same with ±10 megapascal difference, but the displacement can be seen to almost double when comparing to steel and titanium and copper. We think that this is because of the elastic modulus for the material. As shown in the formula on the left, there's a deflections formula, and by keeping the dimensions and the loading conditions of the table being the same, the only variable in this formula is the E, which is the elastic modulus. And here is shown the elastic modulus for all 3 of the materials, and with steel being the highest, we would most likely choose steel to minimize the displacement.
This was our total estimated cost for the entire project. The first 2 designs shared the same cost because we used all the same hardware but just tweaked the placement of actuators and thread and rollers. Actuators cost $280, and we had 2 pairs of thread and rollers that cost $750 with an additional $100 of fasteners. For our third design, we're estimating at least $1,000 for each electric sliding actuator, and we would need about 4 to 5 of them, but we would not need any thread and rollers.
So to conclude, our functionality requirements of the project were met, and we believe with using sliding actuators in a metal prototype with the correct hardware, most of our stability issues will be fixed. So in the end, we are confident in our design and that it meets the main requirements of the project. For some referrals, we never got to the point of ordering electric sliding actuators because of the 4 to 6 week lead time. But we do believe that some programming of the actuators will be needed to have the actuators move in unison to smoothly raise, lower, and tilt the tabletop. In some hardware, like bushings, bolts, and casters, will need to be chosen. And then the next step would be to have Brian, our industrial mentor, test the table in a field setting with real patients. Finally, we'd like to thank Professor Shrestha for helping us with the planning portion of this project and how to approach a problem and solve a project like this. We'd like to thank Dr. Gonzala for taking time out of his week to meet with us almost weekly, providing with all of his engineering knowledge. And thank you to Brian and Susan for allowing us the opportunity to work on this project and the space for garage and tools to work. And Susan also made us cookies, so that was nice. And Brian's also mentioned that he'd like to continue this project with future senior groups, and he's a guy I would highly recommend to work with. Any questions?
Thank you. Okay, so we will take a few questions and questions and you can read up. Any questions?
I was surprised not to see aluminum up there as a material choice. That would be typically something like this. I would be thinking steel versus aluminum, not titanium or copper. Why not aluminum?
Because aluminum does not meet our safety factor, and knowing the lasting modulus of aluminum is around like 70 gigapascal, which is like way lower comparing it to steel and titanium and copper. So we just did titanium and copper because titanium is one of the strongest metal, and we would just like to test it out to show.
Yeah, I guess to add on to that, we have noticed like some problems with our SolidWorks, like mating properties or something. So before we kind of finish this and we get our information to Brian, we will test them on them.
And my follow-up question is, if you go back to that slide that you had of beam deflections, right?
Yeah.
E is in the denominator, but there's something else in the denominator as well. So by only changing material properties, you're throwing out a whole bunch of possibilities of ways to optimize your design, right? So use a bigger cross section, different wall thicknesses, all of those affect I, and that has a huge influence on the way things behave.
The cross section of the table is used based on the previous unit design. So like all the cross section for the beams and the top of the table will have the same for us in our design. So
Actually, I agree with Dr. Kevin's comment. You could change the dimensions, keeping the dimensions exactly the same is not a requirement. Right? You could modify the dimensions and, aluminum is a great material for this kind of thing. And so that could be worked out. That's what I thought. Definitely. Because titanium anyway not a common proposal. So obviously you have to go for steel or aluminum, one of those.
And I think that is also, something that we could add to the recommendations is testing, I guess, different wall thicknesses.
Yeah. Okay, any other questions?
Well, guys, do you mind talking about what the challenges that you had with the design, apart from getting a new model, just in general, overview challenge?
I guess initially finding the type of lift that would lower down to 18 inches and raise up to 30 and also tilt to 45. Looking at his previous designs, he had a lot that were they could tilt to 45 degrees, but they couldn't lower down to 18. So that'd be from the ground to the top of the table, and there'd also be a padding on top of that. So I would say initially figuring out like what type of design you wanted to go with is probably our biggest challenge.
So, a question for all of you: what new things do you learn from this project?
I personally learned a lot about SolidWorks and the whole program, I guess, and going through the design process and the testing process of it all.
Yeah, I learned a lot, especially about the inventor, designing, modeling, and especially when it came to moving parts, just having them move in unintended ways as we fabricated it, which we experienced mostly with rotational instability. We weren't seeing a lot of that in the SolidWorks, so it was definitely challenging when we experienced it after fabricating the first model.
Well, I just learned that we should have started this a lot earlier than we did. Yeah, that could have solved a lot of our problems. Because like even to like 5 minutes ago, we were still having problems with this, and it probably would have been okay if we started this earlier.
For me, the thing that I learned is to always name your mates when you're assembling complicated parts like this. Because going through all the mates, checking each one, we look at which part is made properly or not. It's like I should name all.
All right, yeah, thank you. And then if you have any other questions,